your homework. All right, so on page 123, you got to do questions 1 through 3. All right, what is the dense central core of the atom called? That is the nucleus. Number 2, what determines the atom's atomic number? That is the number of protons in the nucleus. And then number 3, what subatomic particle of the atom is found outside of the nucleus? That's the electron. So hopefully you did well on that. All right, for your classwork, remember I said yesterday you need to start learning the charts on page number 116 through 117, learning the periodic table, those particular elements. So on page 116, you're going to copy down the bold, the name for it, so the bold term, and then the atomic symbol for it. So, or the chemical symbol is the technical name for it. So chemical symbol and the element. You're going to do each of the bold ones 5 times. Now remember, your quiz over this, I mentioned yesterday, we're going to be next Wednesday, Thursday, or Friday. It's going to be next Wednesday, so I'm telling you now. So go ahead and start working on it. So on page 116, copy down the bold terms, like the bold name for the element, and its symbol 5 times. There's 17 of them on this page. So make sure you go ahead and pause the video and then go ahead and do that. It shouldn't take you too long. Just write down, like for example, aluminum, Al. So it shouldn't take you that long to do them all. So about 5 to 10 minutes, maybe. It should take you probably less than that. Go ahead and pause the video and then do that, and then come back whenever you're done. Alright, assuming that you've unpaused the video now let's go ahead and let's review over them. I'm hoping these cards show up well enough on my screen. If you have a cell phone, it might not show up as well, so I'll say the chemical symbol for them as I hold them up for it. But because of that, you want to start drilling them. Using flashcards is the easiest and probably the best way to do these at home. So instead of just writing them out, which works for classwork, you want to make flashcards as well, so you can drill them, and your mom or your siblings or your dad or your grandparent, whoever it is, can also drill them with you to help you to learn them. All right, so first one, Cu. What is Cu? Copper. So try to say it before I give the answer. Cl. Chlorine. Au. Gold. He. Helium. B. Boron. As. Arsenic. Mg. Magnesium. PB, this one's a weird one, it's based off its old name. Lead, good job. Students, I believe last year they memorized it as PB and J as like the peanut butter and jelly sandwich, but they memorized it as PB as like the as like a bad type of PB and J sandwich, or a dangerous one, because you should never eat lead. So they would refer to it as like the bad peanut butter and jelly sandwich. If that helps you to remember, if it's something silly like that, that's fine. But do remember that PB, lead. Alright, Ba, barium. Kr, krypton, like Superman's home planet. Al, aluminum. H, hydrogen. Fe, this is based off the old name, iron. I, iodine. And then C, carbon. Ca, calcium. Ar, argon. Alright, let's go through them again. I'll go through them a little bit faster, so see if you can say them again before I say them. So I'm going to go a little bit quicker. Alright, Kr, krypton. Ba, barium. Pb, lead. Mg, magnesium. As, arsenic. Oops. B, boron. He, helium. Au, gold. Cl, chlorine. Cu, copper. Ar, argon. Ca, calcium. C, carbon. I, iodine. Fe, iron. H, hydrogen. Al, aluminum. Alright, I'm going to go through them one more time, so hopefully you're getting close to me, you're beating me every single time. So remember, remember, this is only 17, you have about 35. So make sure over the weekend, if you want to work ahead, that'll probably be best for you. So we'll go through these one more time. Now, if you need more time than this to be studying them, that's fine. Study them on your own or pause and rewind the video a couple of times. So this last one, only give maybe a second after each card. So if you need more time to practice this, rewind this particular part over and over again. All right, Al, aluminum. H, hydrogen. Fe, iron. I, iodine. C, carbon. Whoa. Ca, calcium. Ar, argon. Cu, copper. Cl, chlorine. Au, gold. He, helium. B, boron. As, arsenic. Mg, magnesium. Pb, lead. Ba, barium. Kr, krypton. Alright, so make sure that you note those as we're going through these. So you can go ahead and rewind the video if you need to go back and watch that part again, and that's fine. But make sure you are studying on your own if you're not getting it in the video. Alright, so let's think over what we've reviewed over the past day so far. What is the organized study of composition and interactions of matter? Chemistry. Perfect. Alright, talk about chemistry and history. Who proposed the atomic theory of matter? John Dalton. Good. There are 5 parts to Dalton's atomic theory. What are they? You don't know, look them up in your book. Alright, remember, it's every element composed of tiny particles called atoms. All atoms of a particular element have the same properties. We have different elements that have different elements have different properties because the atoms are different. Atoms of different elements can combine in a specific way to form new compounds, and chemical processes are the result of the rearrangement, recombination, or separation of atoms. Alright, so do you remember that atoms are those tiny little particles? Now he thought back in his day that atoms were indestructible. We know today that's not quite right, but he did good with what he knew. Alright, now remember, an element is composed of a single type of atom. So, like how we looked at this chart, the periodic table, it's made up of elements. So it's the periodic table of elements. So, whenever you have an element of, we'll say, beryllium, this is what emeralds is made of as a side note. So, beryllium is made up of beryllium atoms all throughout it. You look over here at B, remember what is B? Boron. That boron is made up of boron atoms all throughout it. So that's what it's talking about with an element there composed of a single type of compound, a single type of atom. A compound, remember, is 2 or more different atoms hooked together, while a molecule is just 2 or more atoms hooked together. So you can have like a solid bar of gold. Now remember, what's the symbols for gold? Au. So if I have Au, or a solid chunk of gold, I can have gold bonded to itself, or gold stuck to each other. Now, or I could have something like water, where you have 2 molecules of hydrogen, so 2 atoms of hydrogen and 1 atom of oxygen together. It makes 1 molecule, because it's 2 or more, but specifically, it is a compound now, because it's 2 or more different atoms specifically. If I had just hydrogen, like how you breathe it in the air, this is a molecule, because it's 2 or more, because it's 2 or more atoms, but water is a compound, specifically, because it's 2 or more atoms, but now I have 2 or more different atoms. This one has hydrogen and oxygen, while this one just has hydrogen. Alright, so we talked about that yesterday. We talked about mixtures and physical combinations of elements and compounds. They are all mixed together. No, they're not chemically locked in, they're just mixed together. An alloy is a metal mixture like brass, bronze, steel. If you look back on the periodic table, you don't find those elements. Now some of them, like copper, that is an element. But you don't find brass on the periodic table. You don't find bronze on the periodic table. You don't find steel on the periodic table, because those aren't pure elements. Those are alloys, or combinations of elements. Alright, so take notes. So those are metal mixtures. Alright, each element is given its chemical symbol. Make a note though that the first letter is always capitalized. So if you're looking like at gold, Do not write it like that. Scientists use capital letters whenever they're naming a whole compound. Remember, two or more different atoms hooked together. I pointed to gold by accident. Two or more different atoms hooked up together. So the A, if you capitalize it, the scientist is saying this is one atom, and then if you say U, it means this is another atom. So that's part of the reason why when we capitalize the first letter. Looking at the periodic table, I don't think there's a pure A1. Let me just look really quick. I don't remember if there's just a regular A. No, I don't see just regular A1. So a scientist would be really confused because they wouldn't know what you meant by just capital A. There is a capital U though, because uranium is a capital U. So that's the reason why scientists that they use that first and last letters. Don't say it. So, like for example, if you try to draw copper, remember is capital C, lowercase u. Now, if you said C, capital U, scientists think that you mean, okay, capital letter C, that's one atom, capital letter U, that's one atom. Which element does have capital C as its symbol? Carbon. Good job. So that's this one up here. And then uranium, if you look, uranium is, oh, I forgot where uranium was. Oh, you can probably find it before me. Let's see. There it is. Okay, uranium's right here. So scientists would think, okay, whenever you draw it like this, scientists, I think you mean you have copper and uranium together as one compound. No, you met carbon and uranium together in one compound. That's what this looks like, since C stands for carbon and U stands for uranium. If you write them with capital letters, scientists think you're talking about carbon, uranium. And they would think, carbon and uranium are together in one compound? How? But you just met copper. So that's part of the reason why we give them a first letter as the capital letter and the second letter is a lowercase. So scientists understand, oh, okay, so you mean just one atom at that point. So do be careful whenever you're writing them out. Don't make all your letters capital. Only that first letter should be capital and the second letter should be lowercase. Alright, so that's where we left off yesterday, talking on page 115. Your book has the box at the top of the page talking about John Dalton. I'm going to skip reading that for right now. Do make a note of it though, because your book again is just pointing out you can be a good Christian and be a good scientist at the same time for it. So it is really interesting for it. And that is part of the reason as to how come your book's pointing out in particular for him that he was very, 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 very smart as well. So if you read through it, you'll notice, he did some well-known things for it. Now, he wasn't perfect, but he did do some really interesting things. So I'm going to skip this one for now, but do read it. Your book's just pointing out you can believe in the Bible and be a scientist. And this is one of the areas of a good scientist that even secular scientists say was a good scientist, but he believed the Bible, which is different today. Alright, so go over on page 116, talking about the structure of the atom. Alright, so your book points out that Dalton's atomic theory was a milestone, but it wasn't quite exactly perfect. He thought that an atom was indestructible. He thought that was the smallest thing you can get in matter of the universe. Now, he wasn't quite right, because we know now that an atom can be broken down into smaller pieces. There are 3 parts of an atom in particular that you need to know: protons, neutrons, and electrons. So make a note of them as we talk through these. We call all 3 of these subatomic particles because that means they're smaller than an atom. So subatomic, that means lower than or below an atom. So just make a note. So the smaller particles of matter, these are called subatomic particles because these are all smaller than an atom. Alright, so every atom has a nucleus today. So we know this today. Now keep in mind, your book's going to talk about a little bit later on some earlier theories of atoms. Now, your book points out that today that we know that the inside of the atom has this dense nucleus, or this center of the atom. So you have the neutrons and the protons together in that nucleus. We call them, because they are together in the nucleus, nucleons, because that's where they're located. So make a note, nucleons. These are subatomic particles found in the found in the nucleus of an atom. These are protons and neutrons. So make a note, protons and neutrons are both known as nucleons because they are in the center or the nucleus of the atom. So make a note of all those things. So nucleus, nucleons, protons and neutrons. Make a note of all those. Alright, protons. They're called protons because they have a positive 1 charge. So make a note for that one. We actually arrange the periodic table so that way if you have an atom that has 1 proton, that one's first. The next one has 2 protons. The next one has 3 protons, and so on and so on and so on. We call the number of protons in the nucleus of the atom the atomic number. So I'm going back to my periodic table chart so that way you can see it as well. So you'll notice up here, hydrogen. Now your book has this picture as well, I believe. If you want to look for it, or meant to write down where it was and I forgot. Alright, it's on page 131. So if you look on page 131, you can follow along in your book if it's not showing up super well for it. Alright, you'll notice that the picture, it has a bunch of information on this chart. So it's showing you color-coded. First of all, metals are the bluish-gray color, semi-metals are the pinkish color, and the non-metals are the yellowish-tan color. Now it gives you the chemical symbol, so we'll use beryllium as an example. So beryllium has Be, that's the chemical symbol for it. It gives you the element name, so beryllium's underneath it. Then it gives you the atomic mass. Don't worry about what that is right now. I'm just telling you that that's what that number is. You'll notice that in your book, they put the atomic number in the top left. So remember, that's the number of protons. That's super important because the number of protons determines the characteristics of the element. So if you look over here to hydrogen, hydrogen has how many protons? 1. Good job. Helium has how many protons? 2. Looking down over here, lithium has how many protons? 3. I know this isn't hard, but that's the reason why it's arranged this way. Now, you might wonder, well, why is there weird gaps in between it? We'll talk about the reasons why for that later on. But just make a note, though, that if you're going left to right and down across the periodic table, you'll notice that the numbers are getting taller and taller and taller. Now, this particular section is shoved off underneath it. We'll talk about the reasons why, so don't worry about it right now. That's the reason why the periodic table is arranged this way, is based off that increasing number of protons, or the atomic number on the inside. So, the atomic number, remember, tells you the number of protons. Going back to Dalton's atomic theory, now remember, elements are made up of atoms, and elements have the same properties because they are made up of the same type of atoms all throughout it. So, all atoms of a particular element have the same properties. So that's one reason why we know that hydrogen, each hydrogen atom has 1 proton. Now, if it has 2 protons, is it still hydrogen? If it has 2 protons. Going across, you'll notice that helium over here, if it has 2 protons, that means it's a helium atom. And that's why it's that important, because if you have an extra proton, you are going from one whole element into another whole element. So that's part of the reason why we arrange them this way, and that's part of the reason why the atomic number, the number of protons, is so important, because it determines what type of atom it is. So looking at the chart, let's say with the periodic table, or again, if you can't see it very well on the slide, if you want to look on page 131, you can as well. I'm actually going to look on page 131, because trying to look around and see my screen is a little bit hard, so I'm just going to look at the book. I'm going to try to move the mouse to the right spot. Alright, so if you have 22 protons, no, we'll do a different one. We'll do 24. So if you have 24 protons, what element are you? So you gotta find 24, find it. Alright, chromium. So looking over here, it's a little blurry on this thing, but Cr, or 24, chromium. So if you have 24 protons, you're chromium. Let's say you have 92 protons. This one might be a little bit harder to find. 92 protons. Okay, you'll notice it kind of jumps down here to the 90s. So 92, you're uranium. What if you have, let's see, 30 protons? What element are you? You gotta find, okay, here's the 20s, going across 30. So, what element is this? You might not know this one quite yet because it's on page 117 in your book, so you might not remember this one quite yet. Zinc. Good. Alright, so that's the idea with the atomic number, that if I have one proton, I'm hydrogen. If I have two protons, I'm helium. If I have three protons, I'm lithium. If I have four protons, I'm beryllium, and then so on and so on. So that's part of the reason why the number of protons is so important. So that way, if you have, like for example, 6 protons going across the carbon, all carbon atoms have 6 protons. If you have 7, you're not carbon anymore, you're nitrogen. If you only have 5, you're boron. You have to have 6 protons for you to be carbon. So that's part of the reason why that's so important. Just make a note though. So protons, they determine the atomic number. The atomic number determines the identity, or what type of atom that it is. Alright, so a neutron, these are a neutral substance. So protons are positive, neutrons are neutral. So we should be careful for that. So flipping back to this picture. Oh, wrong direction. So remember, protons and neutrons are both in the nucleus of the atom. So you have a positive particle and you have a neutral subatomic particle, and they are hooked together on the inside of the nucleus of an atom. We've already talked about this. What holds the protons and neutrons together in the center of an atom? What force? Strong nuclear force. Good job. And remember, we don't know really why that happens, because a positive substance and a neutral substance should not stick together. So we don't know why, but it just does. So strong nuclear force, it holds the protons and the neutrons together in the center, or the nucleus of the atom. Now remember, what do we call them if they're in the center? What special term? Nucleons. Perfect. Alright, now, can I have a different number of neutrons? Now remember, you can't have a different number of protons, because remember, if I'm going over here from iron, yeah, that's iron. If I go down, that's magnesium. If I go over, that's cobalt. So because of that, sorry, not magnesium, manganese. Wrong M, so Mn, manganese. So because of that, I can't change number of protons. Can I change number of neutrons? Yes, I can. Neutrons, because they're neutral, they don't affect the identity of the atom. Now, they are heavy, they do have mass. If you want to think of it that way, they're slightly more massive, is how your book describes it. But that just means that they have more mass to them. So because of that, they add weight, but they don't determine the identity of the elements. You can have a different number of neutrons. Like for example, we'll just use carbon again because I like carbon. So carbon has how many protons? Looking at the chart, carbon has 6 protons. All carbons have 6 protons. Now, some carbons, they also have 6 neutrons. So a carbon can also have six neutrons. Some carbons, though, they have 8 neutrons, and that's okay as well. So if I have a carbon that has 8 neutrons and a carbon that has 6 neutrons, which one's heavier? Right, the carbon that has the 8 neutrons. Now, are they both still carbon? Yes, so one of them is just heavier or more massive, if you want to think of it that way, because it has a different number of neutrons. But as long as they have that 6 protons, they're always still carbon. So, just make a note for that. We call those isotopes. Atoms that are the same element, like carbon, so they have those 6 protons, so they're still carbon, but they have a different number of neutrons. They're called isotopes. Sometimes you find these out in nature, and that's okay. Sometimes you can make them in a laboratory. That's also okay. Now, the important thing is that you have the same number of protons. Because protons determines the atom type, and that type of atom is what makes up the elements. So that's probably the reason why the number of protons is specific. For the atomic number of neutrons just affects the weight, so it's an isotope. Alright, quarks. Now scientists don't really know what makes up protons or neutrons, but scientists have discovered, to the best of their ability, that it appears like there are even smaller particles that make up a proton and a neutron. I have a moving animation to help show this. So if you look at the top of page 118, you'll notice you have this chart to help describe it. So we think protons and neutrons are made of these substances called up quarks and down quarks. So this one, oh, that's the neutron one. We'll put on this one first. So for this first one, your book is pointing out that they think that the up quarks, that they are that they are 2/3 positive, and they have two 2/3 positive parts and one down quark. And the down quark is a negative 1/3. So they think that there's 3 parts to every proton and neutron. Now, they think that protons are made up of 2 up quarks. So if you have an up quark is a positive 2/3, while a down quark, is a negative 1/3. So if I add up positive 2/3 plus positive 2/3 plus negative 1/3, what am I going to get? You might know, okay, that's positive 3/3, or just positive 1 at that point. So I think my positive 3/3 is in the middle of the box. Oh, there goes my piece of chalk. So, positive 3/3, or positive 1. So that's where they think that the positive 1 charge of protons come from. So again, looking at it at this diagram, you get positive 2/3 plus positive 2/3, negative 1/3. The 2/3, the positive part cancels out the negative part, so we end up with 1 whole charge. So this is the example over what they think the protons look like. Now, again, they're not really these like blue and red colors. Your book just colored them that way. So here's the idea of the neutron. Also made up of 3 parts, but you'll notice it has 2 down quarks. So you have a negative 1/3 plus a negative 1/3 plus a positive 2/3. I'm really messy. Let me fix that. Alright, what does this give you? Right, so for this one, it basically all of it cancels out for it. So the positive, so negative 1/3 plus negative 1/3, that's 2/3 plus a positive over 3. Basically you get a 0 or neutral substance that all cancels out. And so that's what this one's trying to show you. So you get a positive section and then a negative section, and so it cancels it out to where you end up with 0 or no charge at all for it. And so that's what it's trying to show you for this one, to where you end up with no charge or 0 charge. There's nothing there. So that's what it's showing you for a neutron. Now, we've never seen this, but as far as we can tell, this is the best guess or the best theory for how protons and neutrons are formed and what they're made up of. Now, we think that quarks are believed to be held together by a force called the color force, which I know that sounds kind of silly, but that was the name for it. So, the color force, this is a form of the strong nuclear force. Remember, the strong nuclear force holds protons and neutrons together in the nucleus. So they think, okay, if we're having these hold the quarks together, then this must be a different type of the strong nuclear force. So they call this the color force. Again, we're not quite sure if this is exactly right, but it seems like it's the best theory, and based on experiments, it seems like that this is the best guess or the best theory for it. So maybe in the next couple of decades, your kids might talk about an updated version of this. That's accepted then. But this is the best guess as far as we know, even though it seems kind of weird. You make a note though that quarks make up protons and neutrons. And so this is the best guess or the best theory we have for it. Now, if the quark theory is correct, the color force that binds quarks together so strong is that it's so strong that you can't separate them long enough to observe the individual pieces. But as far as we know, this is the best theory. Kind of weird, but this is the best current theory that we have for quarks and for protons and neutrons as to how we think that they work. Alright, so let's get back into it then, talking about the parts of the atom. So do make a note though, protons and neutrons are made up of quarks as far as we know. You don't have to memorize the up quark and what it is, what the fraction is, and then down quark and what its fraction is. Just make a note though that we think that protons and neutrons are made up of quarks, and that they're the reason why you can have a positively charged proton, a +1, while neutrons are electrically neutral. So just make a note for that. So you make a note though that 3 quarks are needed to make up a proton or a neutron, that the color force is what we think is what binds them together. So the color force is what we think holds the quarks together on the inside of a proton or neutron. Alright, so outside the nucleus, you have the electrons. So you'll notice at the center you have the nucleus. Remember, what do you call protons and neutrons? Because they are together in the nucleus. nucleons. So you have protons that have a positive 1 charge, neutrons that are neutral, the electrons, they are a negative charge, or a negative 1 to balance out the proton's positive 1. Now, your book points out this one is very, 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 very small, very tiny. And as far as we can tell, electrons are not made up of quarks. So because of that, electrons are so small that there is nothing that makes them up. So they're as small as they can get. So electrons are extremely tiny. Your book points out, though, that the electrons orbit relatively far from the nucleus, and so because of that, if the nucleus was a marble in the center of a sports stadium, the electrons that would be flying around it would be like dust in the stadium stands. So that's to help give you an idea over how much empty space is on the inside of an atom. Now keep in mind, atoms are extremely tiny. We can't see an atom. So your book draws it like this. But keep in mind, though, this is not drawn to scale. Your book points that out, that okay, if this, the nucleus, was a marble, and I go down to a sports stadium and drop it in the center, the dust motes up in the stadium spinning around, that would be about how far away the electrons would be compared to the nucleus. So that's a more relative size difference. So even though we draw it like this really quick, the electrons are much, much, much farther away compared to the atom, and they're much smaller. So, just make a note though, your book points out sizes that are not drawn to scale. They aren't close together like this. An atom is made up mostly of empty spaces. But even though the proton has a positive 1 charge, the electron has a negative 1 charge, that attraction is still enough to hold them that close. Well, that charge is still strong enough to hold them, even though they are so small, even though they are so far apart. That force, that attraction, is still what holds them together. The fact that the proton has a positive 1 charge, the electron has a negative 1 charge, that's what makes them want to stick together. Alright, so your book points out the typical electrons, so they orbit the nucleus at 100 quadrillion times per second, and they orbit it in these layers, or in these rings. Now technically, they don't stay in these exact rings. So your book points out, though, that they follow unpredictable paths, and they do seem kind of random. But because the electrons are all negative 1 charge, the electrons, since they're all negative 1, they don't like being next to each other, so they will shift and move away from each other, but they're still attracted to the protons in the center. So they're all moving around the nucleus, but they don't want to be next to each other. And so because of that, they'll shift and move around to make sure that they're not next to each other. So your book points out that they're actually arranged in layers around the nucleus because they don't want to be too close to each other. We call each layer an electron shell or energy level. Your book tells you there are 2 different names for them. So an electron shell or energy level. The farther away you are from the center of the nucleus, since these circles are bigger, it can hold more electrons. There's more room for the electron to be in that layer or in that circle. If you're right here in this first layer, now you might be wondering, okay, this is layer number 1. Why is it given K? Why is that not A? That's because the person that discovered it, he didn't realize it was the first layer. He thought that it was the middle one. So since K is towards the middle of our alphabet, he thought, oh, this is a middle one. I'm gonna call it K, and I'll call the closer ones A, B, C, D, E, F, G, or J. Later on, he discovered, nope, that's the closest one. I was wrong. But at that point, you'd already named it K, and everybody else was already calling it K. So it's too late, it's K now. So that's why that one is K, and then the layer is named after it in that order of the alphabet. So K, L, M, N, O. I know it feels weird, but just because the name's stuck, it's too much work to change now. So scientists don't want to change it. So this is the first energy level, K. The second one is L, third one M, fourth one N, fifth one O. So your book's just pointing it out for it. Alright, so your book points out typically there's 7 shells, so there can be a little bit of variation, but typically it's around 7. 7 is about as high as you can get. Now, your book points out there can be more electrons in those higher energy layers or farther away shells. So up here, you can't have a lot of electrons bumping into each other because they're all negative. They don't want to be too close together. So some of them will spread out into that second layer. Now they're still attracted to the nucleus, so because of that they don't want to fly away, but they don't want to be next to another electron. So they'll fill in the energy levels as they go, spreading out more and more. If you're in this last energy level, there can be a bunch of electrons in that one because it's so large, they're not going to bump into each other or be next to each other, if you want to think of it that way. Your if it gives you a mathematical formula to figure this out, so 2n squared, the n is the number in the shell, so in the first energy level, to figure this one out, so n stands for the energy level. I'm going to use the numbers because that's going to mathematically work out. So 2, 1 squared. So 1 times itself is what? 1. 2 times 1 is 2. So that first energy layer can hold 2 electrons. That's it, because they are too close together. So you can only hold 2. The second energy level can hold how many? So going back to this equation, so n stands for the energy level. So the next one, 2. So 2 times itself, 2 times 2 is 4, and then it's 2 times that. So 2 times 2 times 2, which is kind of weird, is what? 8. And so it jumps up from there and it keeps going on and on and on and on and on. So because that m can hold 18, n, or the fourth one, can hold 32. So again, they jump up pretty quick as they move farther and farther away from it. You don't have to memorize that, but just make a note of, hey, the energy layers or the energy shell, sorry, I'm thinking of chemistry terms. So energy level or the electron shells, it can only hold so many electrons. Do you make a note though of this equation, and that could you find the number of electrons if you needed to? So make a note of this, but you don't have to memorize which layer holds how many electrons. Alright, now keep in mind, the number of protons is important. Why? Because it determines the atomic number or the type of element. Now remember, if I have a changing number of neutrons, what do we call that? It's still carbon or oxygen because it has the same number of protons, but it has a different number of neutrons. What do we call it? An isotope. So could I have a different number of electrons? Yes, I can for this one. So if you have an atom that doesn't have an equal number of protons and electrons, we call it an ion. So if I'm going to have a neutral atom of, we'll say, oxygen. Yep, I always go the wrong direction. Alright, oxygen has how many protons? What's the atomic number? Oxygen has 8 protons. So if it has 8 protons and each proton is positive 1, what's my positive charge? So there's 8 protons, a proton equals positive 1. So 8 times positive 1 is 8. This is easy algebra. So if I'm going to have a neutral substance or have an equal number of protons and keep saying neutrons, protons and electrons, how many electrons do I have to balance out my 8 positive protons? Right, I have to have 8 electrons as well, because each electron is a negative 1. So a proton's a whole positive 1 charge, electrons are a whole negative 1 charge. So if I want a neutral substance or a substance to not have any electrical charge, that means I'm going to have 8 electrons as well, because 8 plus negative 8 equals 0. So we call that a neutral substance. It doesn't have a charge. So if I want to have a neutral carbon, how many electrons do I need? Remember, carbon, if you look at carbon has 6 protons. So if it has 6 protons, what's its positive charge? Positive 6. Alright, so if I need it to have a charge of 0, how many electrons do I need? 6, because each electron is negative 1. So that's where this is coming from. So those are neutral substances. Let's say though that I have carbon. So I shouldn't have erased that. Carbon has 6 protons. So carbon has a positive 6 charge. Let's say though I have 7 electrons. So I have a negative 7 charge. Positive 6 plus negative 7 equals what? This is easy math. Negative 1. So this one has a charge. It's a negatively charged atom. We call these ions. So an atom that has an electrical charge because of losing or gaining electrons is an ion. Specifically, if it's negative, like this, it's an anion. If it's a positively charged atom, it's a cation. So let's say you have carbon and it only has 4 electrons. What would the charge of this one be? Right, positive 2. So this one would be a cation. Now remember, let's say though that I have a substance that I want to make my carbon neutral. So rather than adding or subtracting electrons, I say, oh, I'll just make it to where there only has 4 protons. Can I change the number of protons ever if I'm working with carbon? No, because what has 4 protons? Beryllium. So that's my reason why it's always determined a charge is always the electrons moving. You're either gaining electrons or you're losing electrons. You can't lose or gain your protons because you'll jump entire elements. So you cannot do that ever. So because of that, you can only have an electron come or go. So if you're gaining electrons, so if you have more electrons than protons, then you are an anion because you have more negative charge. If you have less electrons than protons, you are a cation, you have a positive charge. Some people, they remember this last year because they remember anion as it has 2 N's, and so it sounds like negative more. They would also remember it as if you turn the positive sign on the side, it looks like X's. This is for people that didn't like cats, so they would draw it as like a dead cat. If that helps you to remember, that's fine. I like cats. So that one's kind of sad, but it's weird enough to where you might remember it, to where the X is, so it might help you to remember dead cat, cation, whatever helps you. Now that's kind of weird, it's sad in my opinion, but if it helps you to memorize it, that's fine. Alright, we'll go ahead and we'll stop there. Alright, your homework for tonight is to finish reading page 119. So read pages 119 through 122. 119 through 122. Answer on page 123, questions 4 through 6. So on page 123, questions 4 through 6. Your parents should have already gotten the email about the background paper, so it'll be due whenever y'all come back. So y'all have a great weekend. Hope you're able to get some rest this weekend after your exams, and you have a great weekend. And I will hope